Good afternoon, everyone. So welcome to the class. And before we start, I want to remind you that we won't have the physical class this Wednesday and Friday. So we don't have the office hour as well. So don't, like, if you want to talk to me or ask me questions, just shoot me the email. Okay. And also as usual, the lecture videos for like Wednesday and Friday's class will be uploaded maybe later today or tomorrow. So remember to check it. Okay, so last time we covered the topic in vectors, right? And also in the hyperplane. So specifically, we talk about the vector space and the definition of subspace and the span, basis, and the concept of linearly independent and also like dependent, and show you how to operate the dot product of two vectors, and also define what is the hyperplane is, and talk about the convex set, the convex functions, concave functions, quasi-concave and quasi-convex functions, etc., etc. And in the end, I show a definition of separating hyperplane, and I told you that actually we can write it as a theorem here, which I kind of I revised the lecture notes here and put it formally. So the first thing we are going to talk about today is to go through the proof of a separating hyperplane theorem. So what is this theorem about? So suppose that we have two non-empty, like AB, non-empty, disjoint, and convex set. So that means there exists a non-zero vectors n here and a real numbers c here, such that for all the point you pick in the set A, you put it in, you plug that into the hyperplane that you find. You will figure out that the number is always smaller or at least equals c, and for the B, then it must be greater than this c. So this inequality suggests that, okay, we can find a hyperplane that can kind of separate these two sets. So this is what this theorem is talking about. Okay, and now we are going to go through the proof here. And actually, you don't need closeness to prove this theorem, but with that is going to make our proof easier. So if you are interested in it, you can actually Google it to see like how you are going to prove when two sets are open. Okay, but for now, we will assume that these two sets are closed, and at least one of it is compact. Okay. And without loss of generality, we further assume that A is the compact set and B is a closed set. Okay. Okay. So first, I want to claim that there actually exists a pair of A and B, which A is from, like A0 is from A and B0 is from B, such that the distance between these two will reach the inf distance of all the paired you got. Okay, so let me draw a graph here. Okay, so we can look at the proof here. So first of all, we pick a random pair from A and B respectively. I will call it, let me see. I will call it A bar in A and B bar in B. Okay. Then, what's the next? So since A is compact, so we can actually draw a closed ball that with the distance epsilon 1 here to cover the whole A, right? And then we also know the distance between A bar and B bar, which is epsilon 2. So we kind of extend that straight line a little bit at epsilon 1 here, and then you draw another closed ball and take the intersections of B and such closed ball, which is S here. Okay. Okay, so that is from here to, okay. That is the step from the beginning to here. And that will also imply S is compact as well. And in addition, we can always find a B bar here because it's non-empty. Okay, right. Then, since the distance function is continuous, so this is your homework. I'm not going to prove it here. And this is a function over the domain, which is a compact set. So that means there must exist the extreme value. Okay, this is the extreme value theorem, which we have proved it before. Okay, so that means there exists a pair, which I denote as A0, B0, that will reach the minimum distance here. So in this graph, that is here. A0, B0 here. Okay. And then you may wonder, like, is that really true? Like, maybe there exists another pair that's called like A star, B star, that somewhere here, somewhere in a set that has an even smaller distance. Okay, that could be. So here, the rest is going to show that, okay, if that is true, then like something weird will happen, which I use the triangular inequality to prove it. Okay, but you can read it by yourself. But that is the intuition here. So that proves the claim one, which A0 and B0 is the will reach the minimum distance over the set A and S here. Okay, and since that AB are disjoint, so that means these 2 points A0 and B0 cannot be the same one. Okay, now we are at here. Okay, and since it is not the same one, we can construct a vectors from A0 to B0 here, and we'll call it the normal vectors n, which is B0 minus A0. Then we can draw a plane that is, how to say that, perpendicular to these two sets. Okay. We'll call it LA and LB here. And we want to claim that any plane or hyperplane between these two planes are actually the hyperplane that we want. So, okay, so how to prove it? So we have another claim here. Suppose we plug all the points in big A into the this hyperplane, then we will figure out that it's always smaller than the C1. Okay, so this hyperplane is N times inter product X equals to C1, and LB is